Hello everybody and welcome back to another video. Today we'll be talking about some basic encryption techniques and implementing some of them in Java. More specifically, these techniques fall under the category of classical cryptography. First of all, what is encryption? Encryption is a way to codify data or information so that it can't be understood by any unauthorized people. You start off with regular information called plaintext and transform it into a ciphertext, usually with some sort of algorithm. This is called the cipher. The idea is to make the ciphertext unrecognizable from the plaintext, yet still decipherable with a key, something that only the authorized people should have. So it's what is used to encrypt the information as well as decrypt it. I'll be talking about two types of classical cipher in this video. The first is called a substitution cipher. The fundamental idea behind this type of cipher is substituting each letter in the plaintext with a different predetermined letter in order to create the ciphertext. A simple example is the atbash cipher. This is performed by substituting each letter of the plaintext with the corresponding letter of the opposite end of the alphabet. For example, A would become Z, B would become Y, C would become X, so on. So moving on to the Java implementation, I have this atbash encrypt method right here. I start with two char arrays, one with the alphabet in normal order, and another one with the reversed alphabet. And then I loop through my plaintext with this loop right here. And for each character, I replace it with the letter on the opposite end of the alphabet. So like I said earlier, A would become Z, B would become Y, etc. Now I just want to show you how I run this. So if I go down to my main method, I can start off with the atbash encrypt of the word computer, and this turns into XLNKFGVI. Now if I uncomment this right here, this is just basically encrypting it and then decrypting it. So I'm basically decrypting the output from the encrypt method. And if I run this, you can see I get back computer. Another example is the Caesar cipher. This one is a little bit more complex than the atbash cipher and replaces letters in the plaintext using a shift of a certain number of characters. The key in this case is the number of letters to shift. So if you had a shift of 3, for example, then the letter A would become D, B would become E, and etc. Implementing this is actually really concise. You just loop through the string and add the key value of the char value of each letter, which effectively shifts the letter. This takes advantage of the fact that chars correspond to numbers and can be manipulated like they are here. The same thing can be done for the decrypt method, just subtracting instead of adding the key. Now we can go ahead and test this in our main method with the word computer and a key value of 5. So first encrypting, you can see it turns into this encrypted text. Now if I uncomment my test for the decrypt method, this is just taking in the output of the encrypt method and then trying to decrypt it with the same key. You can see I get back the original text, which is computer. A bit more complex example of a substitution cipher is the Hill cipher. This is a polygraphic substitution cipher and relies on some basic linear algebra like matrix multiplication and inverse matrices. Each letter of the message is represented by a number between 0 and 25, 0 being A and 25 being Z. You start off with a key, let's say the matrix 5374, and our message can be high, HI. H correlates to the number 7 and I correlates to the number 8, so the plaintext can be represented with the matrix 7, 8. To encrypt the message, simply multiply the key by the plaintext, noting the order, to get the 2x1 matrix 5981. Then take the modulo of each number in the result by 26, so we can find out which number is which letter. If you don't know what the modulo is, it's basically finding the remainder. We get 7, 3. If mapped to letters, this gives us HD. The first letter isn't always the same, that's just a coincidence here. This isn't very secure since it's such a short message, but it's a lot better with longer messages. Now to decrypt, we first take the inverse of the key, which gives us -4, 3, 7, -5. Now we multiply it by the ciphertext to get the 2x1 matrix, -19, 34. Now if we do each term modulo 26, we get back 7, 8. And if we map that back to the alphabet, we get HI, which is our original message. The second main type of classical cipher are transposition ciphers. These generally involve some sort of shift or change of position for the letters in the plaintext. An example of a transposition cipher is the rail fence cipher. The idea behind this cipher is to arrange the letters of the plaintext in a sort of zigzag pattern. Each row is called a rail, and the number of rails is the key. It's easier to explain with an example. So let's say we have the message computer, and a key of 3. The text would be arranged like so. This gives us the ciphertext CUOPTRME. Now decrypting is pretty easy, because the format of the rails is the same every time, and with the key we know that the number of rails is 3. So you can just recreate the rail pattern, the right amount of rails, and find the original message again. This makes it pretty insecure since it can be guessed after a few attempts of different rail numbers. The route cipher is another example of a transposition cipher, but is more secure than the rail fence cipher because it has more key combinations. For this cipher, the key not only specifies the number of columns that the plaintext letter grid has, but also describes how to create the ciphertext from the grid. Again, this is best described in an example. So let's start with the plaintext computers, and have a key of 3 columns and instructions to move from the top right of the grid, then move counterclockwise. That last part probably doesn't make sense right now, but I'll explain. Now first create a grid with 3 columns with the letters of the plaintext. Now to make the ciphertext, start at the top right, so the first letter will be M. Now move counterclockwise in a circle, giving MTSREPCOU as the ciphertext. To decrypt, write out the ciphertext with the correct number of columns. But since you know the position of the spiral pattern used to create the cipher, just follow that, and you should get back to the original plaintext grid, with which you can find the plaintext. The final example I'll be going over is the columnar transposition. The key is a word, which is then converted into a number of the same length. The number that corresponds to each letter represents its alphabetical rank compared to the letters in the word. Note that if 2 letters are the same, the order in the word should dictate which gets which number. For example, if our key is computer, that will turn into 143-587-26, because C is the first letter in the alphabetical order, followed by E, then so on. After this, arrange the plaintext in a grid, with each column corresponding to one of the numbers in the key. For example, if our message is encryption videos, the grid would look like this. To create the ciphertext, add each column in the order of the number on top of it, so the grid shown would turn into the following ciphertext. To implement this in Java, the first thing you need to do is convert your string key into numbers. So here we have our key, which is an input, and we use this method key2num to convert it into a number. You can see here that I use 2 loops to do that, and I return back a string, even though it's numbers, just so it's easier to isolate the numbers later on. And after I do that, I use this helper method called createEncArray, which is create encryption array. So this method takes in the number key as well as the plaintext and converts that into a 2D array of chars. The first thing we do is find C, which is the number of columns. If the plaintext divides into the key evenly, that's just the plaintext divided by C. And we add one more to make sure that there's room for the key numbers. If it doesn't divide evenly, we add one for the key numbers as well as another one so that we make up for whatever decimal was truncated. Because as you might know, when you divide in Java, the decimal is truncated if there is a decimal. So that always means we basically have to round down, and so to account for that, we add an extra column. So using our RNC, which is row and column, we create a new 2D chart array, then we loop through it and set every value to tilde. We do this so that in case the plaintext doesn't fill the array fully, there's no empty spaces. And after that, we loop through the array and add both the key and the plaintext. Now that we have that, we use a nested for loop to create our ciphertext. You may be wondering why we add 49 right here. This is just because each char value has an associated number, and so in order to get the I to correspond to the char value that is 1, 2, or 3, we need to add 49. For the decryption method, we once again start with getting the number key from the string key. The same method as before is used to find the number of rows and columns for the array. The length of the segments used to create the ciphertext is found, and then the encrypted string is split into segments and stored in an array. That's the segments array. The segments are then stored in the main encryption array, and then the decrypted string is created, and the letters from the array are added to it to create the plaintext. So I went ahead and set up my main method with some examples here. So the first one encrypts encryption videos as the plaintext with the key computer. The second one decrypts that. So if I go ahead and run it, you can see I get the exact same ciphertext as I did in the example, and then of course I get back the expected plaintext when I decrypt it. So yeah, I hope you enjoyed the video and were able to learn something new about encryption. Thank you for watching, and I'll see you in the next video.